In this video, we're going to look at integration by parts. We're going to recognize when to use integration by parts, fingers crossed, and use integration by parts to solve integration problems, and use integration by parts for definite integrals. So we know with the product rule that if we have the function h of x, which is the product of two other functions, f of x and g of x, when we do the derivative of h of x, it becomes the derivative of the first function multiplied by the second plus the derivative of the second function multiplied by the first. Now, if we were to integrate this, g x f prime plus f of x g prime of x dx, and that means that h of x, if I were to undo this integration, so the antiderivative of h prime of x is h of x, which is equal to the product of f of x plus g of x, or times g of x, which is the integration. If I break this apart, because I can do that with integration, the integration of the first term plus the integration of the second term with respect to x, we get this. If I were to solve for f of x g prime of x, I would have this, which is f of x multiplied by g of x minus integration of g of x f prime of x dx, with some u and v replacements and some u substitution and some v substitution, we'll end up with u dv is equal to uv minus integration of v du. You're like, and how does that help me? Well, let's go through some example. Here is integration by parts. This is the theorem, integration by parts. And latte is what's going to help you. A good old cup of coffee, a latte. So when you make a choice, how do you choose which one is u and which one is dv? So usually u is going to be the log first, then the inverse trig functions, then algebraic functions, and trigonometric functions, exponential functions, in that order. So you can have a cup of coffee. Sit back and have a cup of coffee. And that's going to help you choose what a good u is and what a good dv is. So if we let u equal, going down this logs, inverse, algebra, trig, exponentials, obviously the algebra, which is x, is going to be a better choice than sine. So we're going to let u equal x, and du would equal dx. So I choose that this is u. That means this and dx is the dv. So dv must be equal to the sine of 2x dx. That means v must have started out with a negative cosine, 1/2, the negative cosine of 2x. So that's what v must have been. So, by integration by parts, this becomes the integral of the u dv is going to be u, which is x, multiplied by v, which is negative 1/2 the cosine of 2x. So here is my u, here is my v, minus the integral of v, which is negative 1/2 the cosine of 2x, multiplied by du, which is dx. So once again, this is v and this is du. So you can see that I have the integration of uv minus the integration of v du. That's what the integration of u dv is. Now, for the first term, we know this is just going to be negative x over 2 the cosine of 2x, so that's nice. And then I have a minus minus, so it becomes plus 1/2 the integration of the cosine of 2x dx, which is negative x over 2 the cosine of 2x, plus 1/4, because of the fact that when I find the antiderivative of the cosine, that is the sine, but then I needed a 2 there, so it must be 1/4, the sine of 2x plus c. And this is my final answer. Let's take a look at my next example. Going down the form here, I know that I'm going to let u equal, I'm going to sit back and have my cup of latte. Logs go first. So u is going to be the natural log of x. And du is going to be 1 over x dx. That means dv has to be 1 over the square root of x dx, which I'm going to write as x raised to the negative 1/2 dx. That means v must have been a, let me see, so if I undo this, so I'd add 2 over 2 and then divide by that. So then v must have been 2 x raised to the 1/2. So this then becomes, by the integration by parts, it's going to be the 2x raised to the 1/2 multiplied by the natural log of x. So there's my u multiplied by v. And then minus the integration of my v, which is 2x raised to the 1/2 multiplied by 1 over x dx. Just going to erase this now that we've got the u's and v's. Now there's nothing to do with the first term. This is simply just going to be 2x raised to the 1/2, the natural log of x. On the second term, you can see that this x to the 1/2 and this cancel, so it becomes x raised to the 1/2 in the denominator. It's a terrible 1/2, which means that minus, I'll bring that 2 out. This is x raised to the negative 1/2 and dx. So to undo that, this is going to be 2x raised to the 1/2, the natural log of x. And once again, you know this 2 over 2 is really not there. So I end up with a positive 1/2. Divide them by that positive 1/2 gives me another 2. So minus 4x raised to the 1/2 plus c. And that is my final answer. So with c and d, again, I'm going to sit back, have my cup of coffee. Logarithmic functions, inverse algebraic functions will come before exponential functions. So that means this must be my u. So let u equal x squared, and du is equal to 2x dx. dv is equal to e to the x dx. That means v is equal to e to the x all day long. So then this becomes x squared e to the x minus the integration of 2x e to the x dx. Excuse me. Now, we're not done. We're going to have to do this again. So I'm just going to erase this because I'm going to have to do this uv again. Excuse me. I'm sorry about that. So now I'm going to do this again. I'm going to say, okay, let u equal 2 to the x. du is equal to 2 dx. And I'm going to say, let dv equal e to the x dx. That means v equals e to the x all day long. So then this becomes x squared e to the x minus. I'm going to have my new u, which is 2x. I'm going to have my, I'll do that in green. I should probably do that in green. I'm going to have my new u, which is 2x. I'm going to have my new v, which is e to the x, and then minus the integration of my du, which is 2 dx, multiplied by my v, which is e to the x dx. So you see I had to do the integration by parts twice. Now when I get done, I'm going to get x squared e to the x minus 2x e to the x minus 2e to the x, and then plus c. So this is my final answer, and notice how when you do integration by parts, it doesn't always shake out the first time. So not much of a difference between D and E, so I'll go ahead and pause this at this point, and then I'll give you the answer. So pause it now, see if you can do it, and then I'll give you the answer. So this ends up becoming 1/4 e, actually, I'm going to write it with my x squareds first. 1/4 x, the quantity squared, e to the 4x, minus 1/32 x e raised to the 4x. And actually, this should be 1/8. And then I have minus actually that'll be a plus 1/32 e raised to the 4x plus c. And that's my answer there. Okay, looking at e, of course, I'm going to go through my integrations here and which ones I'm going to do. So logs go first, inverse trigs, algebra, trig, exponentials. So f and e I'm going to do similarly. I'm going to let u equal the sine of the natural log of 2x. And then I'm going to let dv equal just dx. du is going to equal the cosine of the natural log of 2x multiplied by 1/x. Then v is equal to x. Now this is kind of weird. Okay, so then this becomes the x, which is my v, multiplied by my u, which is the sine of the natural log of 2x, minus the integration of x multiplied by the cosine of the natural log of 2x multiplied by 1/x dx. Forgot my dx right there. Don't forget that dx. Okay, now what you can see is that this x and this x cancel, and I kind of almost am back to where I started. So let's go ahead and do the u sub again. So uv sub, I should say. And now I'm going to let u equal the cosine of the natural log of 2x. That means du is going to equal 1/x, the negative sine of the natural log of 2x, dx. And now my dv equals dx. That means v is equal to x. So I have x on the sine of the natural log of 2x minus. Inside of here, I'm going to have the x, the cosine of the natural log of 2x, minus the integration of the negative 1/x, the sine of the natural log of 2x. This is my green du. And then multiplied by x dx. That's also part of the du. Now, once again, you can see these x's cancel. All right. So where I am is so let me start with the beginning here. I have the integration. This is the integration of the sine of the natural log of 2x dx is equal to x, the sine of the natural log of 2x. I'm going to pull my negative through, so I have minus x, the cosine of the natural log of 2x. These two were negative, and a negative becomes positive, and that negative out there makes that a negative. So it becomes the negative of the integration of the sine of the natural log of 2x dx. Now, notice how these two match. So what I'm going to do is I'm going to add the integration to both sides. So I end up with the integrations of the sine of the natural log of 2x dx, which is equal to x, the sine of the natural log of 2x, minus x, the cosine of the natural log of 2x plus c. Now I'm going to divide everything by 2, and so the integration of the sine of the natural log of 2x dx is going to be 1/2 x. The sine of the natural log of 2x plus 1/2, and that should be a minus, excuse me, that should be a minus, minus x, the cosine of the natural log of 2x, plus c divided by 2, which is still a constant. This is your final answer. So notice how I had to do my integrations twice, and then I stopped when I realized that this term on the right-hand side matches this term on the left-hand side with a minus sign. So if I add it to both sides, bam, I can solve for the integration, which is odd. I know, it is like odd as odd, and that's okay. The first time you see it, it's really weird and it feels wrong, but it's right. We're good. All right, so I am going to erase this so I have space to do the next one. So hopefully you wrote that down. If you haven't, backspace and write that down. All right. So let's go ahead and look at, let me lock this again. Let's go ahead and look at the next one. All right. So we're going to let u equal the sine inverse of x. And that means dv is equal to dx. And we can do this. This is totally fine. Now, then du is going to be 1 over the square root of 1 minus x squared dx. And dv gives me dx, which means v is equal to x. That means this integration of the sine inverse of x dx is going to be equal to the sine inverse of x multiplied by the x, there's my uv, minus the integration of x over the square root of 1 minus x squared dx. And this is a nice u substitution. So we say let u equal 1 minus x squared du is equal to negative 2x dx. And so negative 1/2 du is equal to x dx. So then this gets replaced with a negative 1/2 du. This gets replaced with u. So this is equal to x, the sine inverse of x, minus the integral of a negative 1/2, 1 over u raised to the 1/2 du. So x, the sine inverse of x, plus the plus 1/2, I'm going to pull that 1/2 out front, plus the integration of u raised to the negative 1/2 du. So I'm going to add 1, so 2 over 2, which means that I end up with 1/2, multiplying by the reciprocal of 1/2, which is 2. This is going to give me x, the sine inverse of x, plus 2 over 2 u raised to the 1/2 plus c. So x, the sine inverse of x, is equal to, not equal to, plus 2 over 2 is 1, the square root of 1 minus x squared, don't forget to back sub, plus c, and this is my final answer. Now what happens when I have limits of integration? Well, when I have limits of integration, so it's a definite integral, then I evaluate, I still do my UV stuff, I evaluate the first piece, and then I do the integration with the same limits and evaluate the second piece. Notice I don't have to change my limits of integration unless I do a, quote, true U sub. This is integration by parts, so I don't need to do that. So as usual, we're going to let x equal u, let u equal x, so I'll write it that way. let u equal x, du is equal to dx. dv is equal to e raised to the negative 2x dx. That means v is equal to negative 1/2 e to the negative 2x. So then this is the integration of x multiplied by a negative 1/2 e raised to the negative 2x. This will be evaluated from 0 to 1 minus the integration evaluated from 0 to 1 of the negative 1/2 e to raised to the negative 2x dx. So I'm just going to erase this. Gives me some space to work below and looks kind of messy. So starting with the upper limit, I'm going to do this evaluation right here. So I'm going to do this evaluation, and it's going to become negative 1 multiplied by 1/2 multiplied by e raised to the negative 2 minus 0. So this becomes negative 1/2 e raised to the negative 2 minus. And I'm just going to do my regular integration here. And so this negative becomes a positive. However, when I integrate this, I'll need to have a negative again. So it's a negative 1/4 e raised to the negative 2x, evaluated from 0 to 1. Negative 1/2 e raised to the negative 2 minus 1/4 e raised to the, I should probably put that in parentheses, e raised to the negative 2 minus 1/4 e raised to the 0. So I end up with negative 1/2 e raised to the negative 2 minus 1/4 e raised to the negative 2 minus 1/4. I can clean this up a little bit. Same common denominator, so I have negative 3/4 e raised to the negative 2 minus 1/4, and I can leave it like that. All right, so let's take a look at my next example here. I'm going to let u equal x, du is equal to dx, dv is equal to the cosine of x dx. Don't forget the dx. V is equal to the sine of x. So then this becomes the integration of u, which is x, v, which is the sine of x, evaluated from 0 to pi, minus the integration evaluated from 0 to pi of the sine x multiplied by the dx. Okay, so once again, we're going to evaluate. So when we evaluate at pi, I'm going to have pi times the sine of pi minus 0. So that's just going to be, the sine of pi is 0. So this actually goes to 0. So this whole thing goes to 0. And then minus the integration of negative sine is positive cosine of x evaluated from 0 to pi. So I have 0 plus the cosine of pi minus the cosine of 0. So the answer is negative 2. Let's take a look at our last example here. So I'm going to let u equal the natural log of x squared plus 1. And du is going to give me 1 over x squared plus 1 multiplied by 2x dx. dv is equal to dx. So then this integration is going to go from 0. This integration, not going from 0, will be the u, my u, which is the natural log of x squared plus 1, multiplied by my, I didn't finish this, and then v is equal to x, multiplied by my x, evaluated from 0 to 3, minus the integration of 1 over x squared plus 1, and that should be 2x over x squared plus 1, multiplied by another x, dx, dx. All right, so this is a nice evaluation, so let's just talk about this one, and I'll let you finish it on your own. So this is going to be 2x squared over x squared plus 1, and so this is going to be 2 multiplied by x squared over x squared plus 1, and what we're going to want to do is long division. So I'm going to take x squared plus 1, and it's going to divide into x squared plus 0x plus 0. So we know that this happens to be 1, so 1 will go there. So I have x squared plus 1. I'm going to subtract this off, and so I get negative 1. So I get 1 plus negative 1 over x squared plus 1. So this becomes 2 multiplied by 1 plus negative 1 over x squared plus 1. So this piece, this portion, I'm just going to erase this so I can have the space and just talk about this part of the integration. So then just this part of the integration, just this part, the integration here, I'm going to pull out that 2. And this ends up becoming 1 minus 1 over x squared plus 1 dx. This is a nice, easy integration. This is just going to give me x. And this is the derivative, I think, of tangent inverse. So I can do the tangent inverse there. And notice I don't have to change my limits of integration. So I just wanted to talk about that. For D, I'm not going to go through the integration, but I will give you part of the answer. This is going to give you 5x multiplied by x divided by the natural log of 5 evaluated from 0 to 1 minus 5x over the natural log squared of 5 evaluated from 0 to 1, whatever that ends up becoming. And then for E, you end up with 2 e raised to the square root of x multiplied by the square root of x evaluated from 0 to 1 minus 2e raised to the square root of x evaluated from 0 to 1, and then whatever that ends up being. So if you need to go over any of these in class, absolutely we will. Otherwise, we'll see you in class.